to the next installment of Mathematics Olympiads. Right now, today's problem is shown here. Let's you can read it up. Okay. Now, as usual, if you like what you are looking at, do subscribe and then press the notification bell to receive the latest video. Okay. Now, the first problem is quite a warm-up problem here. Find the real solutions to the equations. So real solutions mainly means the x and y must be all real numbers. Okay, so that's our objective today. Now there are many ways to do this. Of course, your first impression is to actually expand this. Yes. If you expand this, we will not be able to reach any conclusion. For instance, just let me show it to you. So if we expand both sides here, we will get right. So this is what we have, and then some of you might have that idea of moving everything to the right hand side. Okay, to the left hand side. Sorry. Okay, maybe we can give that a try. Maybe it works. Okay, let's see. If it doesn't work, then I'll show you another alternative ways of solving this. Right. So we have here. If we move it over, it will be x y. Okay. So by far, this is the one that we have here. Okay. And then maybe some of you have that idea of completing the square, right? So because this is algebra, so we can give it a go. So for instance, here we have plus y square minus y plus xy plus 1 equal to 0. All right. Okay. Let's give it a try with completing the square in this case. All right. Now, before we can complete the square, is kind of challenging to complete the square here because most probably you're going to get some fraction and so on. So maybe we can try something like this, for instance. So we can say that this is a half. For instance, this is just something that we introduce to manipulate the expression here. So I can say that that is the same as x squared plus 2x here, and then plus what we have here, we have another x squared. Okay, for instance, another x squared plus with a y squared minus 2y, and then of course we have another y squared here. Okay, another y squared, and then finally we have something like this plus 2xy, for instance, and then plus 2 here. So take for instance, if we try to re-describe or restructure this expression, it will look something like this. So just let me check one more time whether I get all the expressions correct. Okay, I have that. Okay, the y square is okay, and then the x square, the x and the y is okay, and then the xy is still okay, and then the 1 is a 2 there, right? So at this point, I should be ready to complete the square. Let's give it a go. So for instance, here I will have x plus 1 square minus a 1. That is the completing the square for this first part. So maybe I'll put a bracket across here so that we can recognize that. And then next we have the x square and y square. We can't we can't do anything, so I'll just combine them together. And then here we can perform the completing the square, for instance. And then yet there is another 1 there, so I'll put another bracket across where I have completed the square in this case. And then finally in this case I have 2xy plus 2. Okay, so that's what I have currently. And then by simplifying, of course, if I simplify this, I would be able to get, let me see, what do I have here? This is a -1, -1, so -2. That can be cancelled out. So all I have is x plus 1 square plus y minus 1 square here. Okay, and then now this one x square plus y square only left with x square plus y square, or maybe I'll rewrite in this form so that it's easier for you to recognize what I'm going to do next. So in this case you will see xy plus a y square. Okay, so you can see that this expression here we can factorize that quite easily. Therefore we have x plus 1 square plus y minus 1 square plus this one can be described as this equal to 0. Right? Okay, so at this point we can now I'm going to rewrite over here so it's easier for us to refer rather than me changing it to somewhere else. So at this point you can see that we can rewrite this as x plus 1 square plus y minus 1 square plus x plus y square here. Now you notice that all these terms are positive. Now the only way we can have solutions for this is I would say the only solution that we can get is when this one is equal to 0 and at the same time this one is equal to 0 and at the same time x plus y is equal to 0. So that's the only solutions that we can have to ensure that the whole expressions would yield a 0. And then therefore we can conclude that x is equal to -1, y is equal to 1 here. And then that actually is being confirmed by the last statement. Here we can see that x is actually equal to a -y, which is indicated here. Now that is our solutions. I hope that is clear to all of you for first question. Alright, I will continue to the next problem in a short. Next problem, as I mentioned before, there's another alternative methods to solve this, which was suggested by one of the mathematicians. Right? Now I'll try to show that alternative methods here. So in this case, we will let u equal to x plus 1, and then let v equal to y minus 1 here. And then by rearranging, so for instance, in this case, we can say that x is u minus 1, whereas y is actually v plus 1 here. Right. And then once you are satisfied with the structure, we are going to substitute this structure here into equations number 1. That would yield this. There's a x, there's a y here on the left hand side, which is the same as u multiplied with v here. And then you notice that this is actually uv, right? And then as usual, you can expand this, but expansion in this form is much more easier than the one that I showed to you just now. So in this case, we have this, and then 2uv minus uv equal to 0 here, right? And then from here, you will notice that we have UV plus UV here because of the subtraction. Okay, and then by applying the same strategy, we will be able to have this. Okay, so it's the same strategy here, and then by using divide and conquer onto the expression here, so we can write this as v squared plus u squared plus 2uv plus v squared. Okay, now from here we will reach the same conclusion as before, but rather the format is a bit embedded. Okay, so that's what we have, and then we can conclude that the only solution for this expression here is when u is equal to 0, v is equal to 0, and at the same time u plus v must be equal to 0. And then since we describe u as x plus 1, therefore x plus 1 is equal to 0, with u x equal to -1, y minus 1 is equal to 0, and then that will u y equal to 1. And then at the same time, in this case, we have u plus y, which is actually x plus y equal to 0, and then that will yield the last confirmations that this result is actually true, and then therefore that complete the real solutions in this case. Right? I hope that is useful. I'm going to show you the next problem. This is the second problem, is a trigonometric problem to be precise here. Okay. Now, if you look at the angle that is given to us is not something that we use to work with. So the best way to analyze this or prove this trigonometric equation is by generalizing it, right? So to do that, we can let theta equal to 180 degree divided by 7. So we can let theta equal to this, and then you will notice that this is actually 2 times of theta. This is 2 times of theta. This one will be 3 times of theta. Let me see, the 3 times 3. Yeah, correct. So this is 3 times. So the whole expressions can be rewritten as CSC cosecant. Just let me write these notations so that we are clear what we are looking at. So this is actually cosecant. So we can write this as cosecant theta is equal to just let me use the same notations here. Cosecant 2 theta plus cosecant 3 theta. Now, if you are not very familiar with working with cosecant, we can convert everything to sine or cosine. But anyway, cosecant is the reciprocal of sine theta. So we will rewrite this as sine theta. Okay. And then, of course, I'm not a fractional person, so I tend to reduce everything, all the fractions, so that it looks like an integer equations that is a linear equation that is rather easy to solve. So here you can multiply with sine theta, sine 2 theta, and sine 3 theta on your left hand side and on your right hand side here, right? So by doing so, we have here this part will be sine 2 theta, sine 3 theta equal to, in this case we will have a sine theta, sine 3 theta plus another sine theta. Sine theta, is it sine? Let me see. Sine theta, yes, correct. Sine theta, sine 2 theta. Okay. And then we notice that we can factorize this, so I can write this one down as sine theta. Um, if I arrange them in a particular order, so sine 2 theta plus sine 3 theta. Okay, now that's what we have here. I'm going to make a marking there. This is what we are going to prove. Instead of proving this, we are going to prove this. By proving this one here, by proving the double star here, imply that we are able to prove this. Okay, now that will be our strategy here. Okay, now before we continue with this one here, we need to take note of yeah, let me write down. So take note of one result that we can explore here, right? So one of the result would be that we can discover here. Right now, I'm going to write down one of the result that we can make use of this in order to prove this section here. So we notice that 3 theta plus 4 theta. Now I need to remind you again, the theta that we are referring to is this value. So if we take 3 times of this value, end up with 4 times of this value, that would actually be, so if I try to show it here, that will be 5407 by 7207. That is indirectly a very beautiful result. Okay, now that requires a bit of experiment if we are beginner here, right? Like me. Okay. So from here, we can rearrange this. We can rearrange this as 180 degree minus of 4 theta. Now, knowing that the relationship between 3 theta and 4 theta, we can say that in this case, sine 3 theta is the same as sine 180 degree minus of 4 theta, which is indirectly the same as sine 4 theta. Now, you can actually prove this using compound angle identity, or you can make use of your understanding of the second quadrant. Sine would also give the same result as sine 3 theta in this case. Right? So no matter how, you should be able to reach this result here. Okay, so why is this important? Because we have sine 3 theta here. So sine 3 theta is indirectly the same as sine 4 theta. Therefore, this statement here, I can rewrite the statements that we're going to prove. So I'm going to rewrite here. So this statement, the double star here, I can rewrite as my left hand side is actually equal to sine 2 theta sine 3 theta, whereby my right hand side I can rewrite as sine theta sine 2 theta plus sine 4 theta. Okay, so this is exactly the same as this statement here. So if I'm able to prove that left hand side is the same as right hand side, now I will be able to prove this this equation. Knowing that this equation is correct, it will imply that this equation should be correct also, right? Now that will be my intention. Now why using this is easier than using that sine 2 theta plus sine 3 theta is because we can make use of the additions and subtractions identity. Right? Now I'm going to show you how that identity works. Okay. Now in this case, my focus at this point will be to simplify this sine 2 theta plus sine 4 theta. Okay. Now my strategy will be here. I'm going to let P plus Q equal to 4 theta, and then P minus Q be 2 theta here. Right now I have number 1, number 2. Of course, you can solve this simultaneously to obtain your P and Q. Right now, I'm not going to go through how to solve this simultaneous equation. You can try it out. So if you solve this, you would reach these conclusions where the P will be 3 theta and then the Q would be theta. That shouldn't be a problem solving that too, right? So that part I'll leave it to you. Okay. Now once we have this, we can come back to our objective. Our objective is we want sine 4 theta. I want sine 4 theta. So how do I get sine 4 theta? My sine 4 theta is the same as sine P plus Q. So sine 4 theta is the same as sine P plus Q. And then by using the compound angle identity, all right, now by using compound angle identity, I can actually expand this. Okay, now, okay, hopefully I have enough space to write here. So I'm going to write down that sine 4 theta is the same as sine P cos Q plus sine Q cos P. Right. Now that will be my, yeah, maybe let me call this my first main equation. And then the second one, sine 2 theta. So sine 2 theta, I can make use of this. So expanding that, I will be able to get sine P cos theta minus sine Q cos P here. That will be my second equation. And then because I want to obtain the addition here, so if I sum up 1 and 2, I would be able to get, so since I sum 1 and 2, I will only get sine 2 theta plus sine 4 theta must be the same as 2 sine P cos Q. This is Q, so Q, right? And then what is my P and Q? My P and Q is this. So therefore, I can write this as sine 3 theta cos theta here. Right? Now you can see that these whole expressions, additions, would turn into multiplication. And then therefore, we can conclude our results now. Right? Now I'm going to erase off this section here so that I can work with this. Okay, I'm going to write at this section so it's easier to retain the rest of the informations here. Now we are at this point here. We have proven the summations of this. Therefore, from here, I'm going to write down my right hand side is the same as sine theta multiplied by 2 sine 3 theta cosine theta. Okay, now that's what we have. And then that will be the same as, let me see. So that will be the same as sine 3 theta. Okay, so I'm going to write down there. There's 2 sine theta cos theta sine 3 theta. And then by using double angle identity, we know that this is the same as sine 2 theta sine 3 theta. And then indirectly, this is the same as my left hand side expression. You can see that here. So therefore, this equation here has been proven. Knowing that this is true, therefore we indirectly has proven this. Alright, now I hope that is useful for your learning at this point, right? Okay, now before that, let me try to draw our partitions for you to refer where we are. So this is a staircase that we need to follow, right? So I hope that it's clear. I will be showing you the next problem in a short while. Third, math problems. Okay, now let's read through. In this case, we let a, b, d, x be all real numbers such that the x is not the same as the multiple of k pi, where the k are all integer numbers, and it satisfies this equation. So our main objective here is to prove that a cube bracket 4b square minus d square is equal to b to the power of 4, 3a minus c. So that's our intention here. Now we can start by in this case is rather tough, but we know that the idea behind this is we know that all this ratio is a constant, so we can label this as a constant, for instance. If you like, you can label this as lambda as a constant or any symbol you like. So knowing that this is a lambda, so all this ratio will be the same as lambda here. Now I'm going to start by working out sine for x first. Let's apply a bit of trigonometry identity that we knew of. Okay, now because I saw that there are square there, so the motivation is if there are some square related to b and d and so on, most probably we are going to square this expression as well. But before that, we are going to rewrite this as this one can be converted to converted into another trigonometric expression using double angle identity. So I can write this double angle identity as sine 2x cos 2x. Right, now next I can square both sides, so that would actually give me a 4 sine square 2x, and then that will be cos square 2x. Now because there is no cos in my original expression, so I might want to change everything to sine instead. In this case, I can make use of one of the simple identity here, so I can rewrite like this. Okay, so we are almost ready at this point. Just let me rewrite that. So that is sine square 4x is equal to this, right? So now this is where the rest of the ratio become very important. So the first one related to sine 2x. So I'm going to take sine 2x divided by b should be equal to a lambda. Now we know that sine 2x must be the same as lambda b here. And then, as we know, we can just substitute this this section here, number 2, into number 1 here. So therefore, this sine, okay, hold on, just let me. So we know that this sine square 4x must be the same as 4 lambda b square 1 minus lambda b square. Okay, so that's what we have. Just let me check one more time in case I make a mistake here. Right. Now, not only that, not only using sine 2x equal to lambda b, we can express sine 4x also at the same time. Knowing that sine 4x is equal to lambda, so therefore we can also make use of this expression. So from here we know that sine 4x is actually equal to lambda d. Now that will be our third equation. We are going to substitute this one into here, then it will be easier. Now therefore we will have lambda d square should be equal to 4 lambda b square 1 minus lambda b square. So that's what we have. And then simplifying this, I'm going to simplify this one over here, so it's easier to refer. So from here we can rewrite that as d square equal to 4b square 1 minus lambda square b square. Now that will be my quite important equations here. So I'll label that as number 4. Okay, now we are almost there. And then next we can We can perform the same result here. We can start by considering sine. So just now we have considered sine 4x and sine 2x. Now we can consider the sine x and sine 3x. So let us consider sine 3x now. Also require a bit of trigonometry identity. So we're going to make use of the double angle identity. So that will be sine 2x plus x. I'm going to slowly work out the identity. Of course, some of you, if you can remember that identity, you can go ahead and use it. Right? So in this case, that will be a sine 2x cos x plus sine x cos 2x. Yeah, so there's a compound angle identity. And then from here, we can slowly express everything in terms of sine because our ratio are all in sine. So I'm going to rewrite over here, it's easier. So that will be a 2 sine. So there will be a 2 sine x. I'm going to apply a double angle identity here. 2 sine x cos square x. So cos square x can be written as sine square x here. And then the same thing here, I can write as sine x. So cos 2x, I can make use of one of the double angle identity for cos in this case. And then by simplifying, I will be able to get everything in terms of sine. So that will be a sine minus a 4 sine cube x. Let me check, there's a cube, 2 and 4. So that will be my expression. Okay. Alright, so I hope that is clear. And then from here, I will make that remark. We know that sine x must be the same as lambda a. And then at the same time, sine 3x is the same as lambda c. So I'm going to substitute everything here into this expression here. So that will be a, okay, I'm going to substitute into this expression here. That will be a lambda c on the left hand side here. Must be the same as here I will have 3 lambda a minus 4. Okay, so 4 lambda a cube. Now, of course, we can factorize this in a short while, but at this point of time, we have c equal to, we can cancel all the lambda in this case. So therefore, we have, what we have is a 3a. Okay, maybe I can take out the a in this case, if you like. So I can take out the a. That will be a 3 minus 4 lambda square. So it's lambda cube, is it? Lambda, okay, sorry, it's lambda square because one of the lambda has been cancelled off. So that a has been taken out, so that will be a square here. So currently this is what we have. So we have two expressions here, 4 and 5, that we're going to solve them simultaneously. Right? Okay, so just let me clear this up. Okay, last part. Next, we're going to solve these two simultaneous equations. For from number 4, we have to rearrange this one more time. For instance, based on my perspective, I would rearrange it in such a way. I would say 1 minus lambda square b square is equal to d square over 4b square. And then I would say that lambda square b square is the same as 1 minus d square over 4b square here. And then if you like, you can actually write this as 4 lambda square b square is equal to 4. Let me see, 4b square. Yeah, if you don't like the b there, you can just simplify the whole thing. Okay, I might as well just simplify the whole thing here because I'm not a fraction person, so I'll bring all this 4b squared onto the other side there. Yeah. Okay, so that will be a lambda square of 4b to a power of 4. That will be a 4b squared minus a d squared. Now that will be my equation number 6. And then for equation number 5, let's consider equation number 5. Equation number 5 can be rearranged also. We can rearrange it in such a way. 3 minus 4 lambda square a square is the same as c over a. And then therefore we can write down that as a square is equal to 3 minus a. And then of course we can simplify that a bit. There will be a3, 3a minus a c. That will be our equations number 7. And then by solving these two, the main objective here is to get rid of the lambda because lambda was introduced by ourselves. So we have to get rid of this so that we can prove this expression. So we're going to take up to you how you want to deal with this. For instance, you might want to divide. For instance, we take 6 divide. Am I gonna? Yeah, correct. So take for instance, if I take 6 divided by 7, so all the lambda is gone. So we have b4 a to the power 3 is the same as 4b squared minus d squared over 3a minus c. And then finally this can be written as a cubed 4b squared minus d squared is the same as b to the power 4 3a minus c. So indirectly we have proven that this expression is true. Right? So I hope this has been something new for you to pick up, and then a bit of revisions on all the topics that you have learned by far. Right? So if you find that this is useful to you, do subscribe and then press the notification bell. You will have a newly upload videos. You will get notified easily. All right. Thank you very much. I'll see you guys again.